Hey, welcome back to the Idea Mechanics Lab. I'm your navigator, and today we're diving into a really cool idea. What if car parts could actually think for themselves? We're going to use a super powerful innovation tool to see how one simple material can solve a really complex engineering problem, all on its own. Let's get right into it. So let's just start with this one big question. What if we didn't need complicated computers or a bunch of sensors to make things smart? Seriously, what if the materials themselves, the steel, the plastic, the alloys we use every single day, what if they could react and adapt all on their own? Answering that question is the absolute key to having an innovator's mindset. It's all about realizing that the biggest breakthroughs don't always come from adding more stuff, more complexity. A lot of the time, they come from totally redefining our most basic ideas about the materials we're working with. Okay, so check this out. This is the core shift in thinking. The old way, right? It sees materials as static. Steel is hard, rubber is soft, and that's it. That's the end of the story. But the new way, the TRIZ way, asks a totally different question. What if a material could change its properties when the environment changes? All of a sudden, that material isn't just a passive object anymore. It's an active part of the solution. And this brings us right to a core idea from TRIZ, which is just an amazing problem-solving system. It's Principle 35. Parameter changes. The whole idea is actually pretty simple. Instead of fighting against changing conditions with more and more engineering, we design materials that are smart enough to adapt with them. We literally change their fundamental properties, like their shape or their flexibility, so they can work with the environment, not against it. All right, enough theory. Let's put this principle into action. We're going to head into the world of cars to look at a classic engineering headache I like to call the great airflow battle. It's a perfect example of what engineers call a technical contradiction. So here's the heart of the problem. When an engine is cold, you actually want to restrict the airflow. You want to choke it off a bit so the engine warms up fast and runs efficiently. But the second that engine gets hot, you need the complete opposite. You need maximum airflow to keep it from overheating. So you've got two totally conflicting needs for the very same part. What do you do? Well, the traditional solution was to just throw a bunch of hardware at the problem. I'm talking heavy mechanical actuators, electric motors, and a whole web of electronic sensors. The thing is, all this stuff adds weight, it adds complexity, and maybe most importantly, it adds a ton of new ways for things to break. It's just a clunky brute force fix. But this is where Principle 35 comes in for the win. It gives us the breakthrough. Instead of adding more complicated parts, what if we just used a smarter material? The really elegant solution here is a material that can just react and change all by itself. And the strategy? It's so simple, it's brilliant. We just eliminate all that external mechanical complexity. Instead of adding more parts, we change the parameters of the material itself, and we make it do all the work. And let me introduce you to the hero of our story today, the Shape Memory Alloy, or SMA. This stuff is incredible. It's a unique metal that can be programmed to remember a certain shape. So when it hits a specific preset temperature, it automatically snaps right back to that original form. It honestly feels like magic, but it's just pure material science. Okay, let's see how this actually works in a car's active grille. In state A, the engine's cool, so the SMA actuator stays in its closed shape, which blocks airflow, improves aerodynamics, and helps the engine warm up. But as that engine heats up, the alloy hits its trigger temperature and, click, it physically transforms, automatically opening up the grille vents to let air in for cooling. No motors, no sensors, just the material itself reacting to the heat. How cool is that? So what's the big result of taking this approach? It is pure, unadulterated innovation through simplicity. We get this really sophisticated adaptive system from an incredibly elegant and simple design. This whole idea actually has a really awesome name, passive intelligence. The system is super smart, it's reactive, but it doesn't need any active power. It doesn't need a computer telling it what to do. It just senses the change in its own environment and does its job.
And the benefits are just huge. I mean, look at this. We've completely gotten rid of the need for motors and actuators. We've reduced the car's weight and stripped out all that unnecessary complexity. And by doing that, we've created a system that's way more reliable because there are just fewer things that can break. It is a massive win all around.
This brings us to what might be the single most important takeaway from all of this. Real innovation isn't just about adding more parts to something. It's about making the materials you already have do more of the work. And just like that, the airflow battle, that huge contradiction between aerodynamics and engine cooling that we started with, is solved. And it wasn't solved with a complex machine, but with a simple, elegant parameter change in the material itself.
So I'm going to leave you with a little challenge. Just look around at the objects you use every day. What other seemingly dumb, static parts are out there, just waiting for the right parameter change to become something intelligent? The next big breakthrough could be hiding anywhere.